Ohm's law from the microscopic point of view. A lot of new things, drift velocity and all will come up. So let's first take a dig at Ohm's law. And this is nothing that you don't know. Voltage varies directly with current, right? So what does Ohm's law state? Ohm's law plainly states that current flowing through a conductor is directly proportional. I drew that diagram, that Kikwala diagram have I drawn? Yeah. So the current flowing through a conductor is directly proportional to the PD that you maintain across the ends, right? More is the PD, more current can go. And why you need that PD? Because there will be one fellow whose name is resistance who will try to strangulate that cross section, right? So Ohm's law tells us that the voltage is equal to V is equal to IR, right? Now say you take one conductor. Let's say we take a conductor. You know the difference. A conductor can be a good conductor or a bad conductor. No one is 100% good conductor. Conductors which follow Ohm's law are known as ohmic conductors, and the plot will be in the form of a straight line. Are those things clear? Right. Still, if you have slight bit of doubt, so if you have any doubt, so it's something like this, and this is, so always remember the equation of a straight line is given by y equal to mx plus c. And if the line passes through the origin, then the equation is y equal to mx. What is your equation? V is equal to Ri, not IR, where R is the ratio of voltage. So on y-axis, we will always have voltage, and on the x-axis, we will have current. And the plot that you will get for an ohmic conductor will always be like this. And conductors which are non-ohmic will not follow this straight line. So whenever you calculate the slope of this VI curve, you will always say that this is giving us resistance. And you know, between two curves, if I tell you which has more resistance, the one which has more slope, as simple as that. But however, if they start to trick you by making it an IV curve, then the one which has lesser slope actually has more resistance. Okay, so let's look at a conductor. Let's say I take a conductor whose length is around L. The length is around L, right? So L length of a conductor. So let's say this is an L length of a conductor. The length of this conductor is L. And then what I do, I add another same replicate piece. Okay, I add another replica piece, which is another L. So now what is the length of my conductor? The length of my conductor has become 2L, right? When the length of the conductor becomes 2L, we always say that the resistance has also become, new resistance has also become 2R, 2 times of R. Another way to say this is a conductor, right? And you are actually, now you have, so we say that the voltage gets added up, whatever was V, and the same current is actually flowing through it. So if your voltage doubles up, in order to keep the equation constant, your resistance also has to double up for the same I. Have you understood? So from here we say that these are all grade 10. Resistance is directly proportional to length. This is one finding. Resistance is always directly proportional to length. Is this understood? Pretty easy. Okay. Then what we do, we look at the cross-sectional area. Cross-sectional area. The cross-sectional area is suppose A. Suppose the cross-sectional area is A. And what you do, you make the cross-sectional area, you reduce A to say A by 2. You have reduced the cross-sectional area from A to A by 2. Just have a look. This was my cross-sectional area, children. This was my cross-sectional area A. It could have been any shape, just for understanding purpose. And I have now made it how much? A by 2. This was A. This is now A by 2. When it was A, more electrons had, what is current? Current is the flow of electrons. More electrons had space to actually go through it. Right? The space is more. When you have reduced the number of electrons, space available for the electrons have become half. Are you getting it? Has become half. So what happens? The current will become half, whereas the resistance will double up. So in this case, the resistance will double. The resistance will double. However, the current will become half. Very easy. Look, Q amount of charges are here in this cross section. If you half the cross section, then the number of charges also get halved up. Okay. So from here we get our ratio. Resistance is inversely proportional to area. These are two findings. Okay, children, today onwards, whatever I'm doing in square brackets, keep writing them. All these things we used to do in grade, if you remember, that in grade 10, we used to say the resistance varies directly to the length and varies inversely to the area. So today we just saw why it varies inversely to the area. Is this understood this much? Right. Is the definition of Ohm's law clear with you? Ohm's law states that the current flowing through the cross section of a conductor is directly proportional to the potential difference maintained across its ends, provided Ohm's law has got a condition, provided temperature and other physical properties remains the same. And what do you mean by this other physical properties is basically the geometric properties. You cannot do chhed-charophi with either the length or the area. Have you understood? If you take a piece of, say, suppose this particular Reynolds pen, this is a conductor. So it has got an inbuilt resistance in it. And I try to pass some current through it. And I keep on measuring I try to connect it to a potential difference source, and I try to find out how much current is passing through it. Okay, a little bit drifting away from this topic. So let's say there is a piece of conductor. How would you conduct this experiment? Okay, how would you conduct this experiment? What I have done here is that I have put a variable resistor. Okay, there's a variable resistor, and I have connected an ammeter to it. And say, for example, I have put a voltmeter to it. Grade 10 basics. So my current is going in this way, this way, this way, this way, this way. Right? This is a typical lab experiment. Just understand. What does a rheostat do? So see, if you are actually bringing the jockey till here, you are using the entire resistance. You are reducing the flow of the current. And if you slide the jockey here, that means you have bypassed the resistance. Okay. So say suppose in an experiment, I do like this. I take some serial numbers. Okay. And I read what is the voltage. Means so I need to vary the voltages. So if I vary this voltage will vary. So I say I have given a voltage V1 to this conductor. And this is my experiment 1. When I pass V1 on the emitter, I am getting a reading A1. Got it? And similarly, I take a couple of readings and say I have got a V5, I get a A5. Now, all these, what I do, I take them on a characteristic. I take my V and I try plotting V1, A1, V2, A2, V3, A3. So in an experiment, if the conductor is ohmic, you will find your points in this manner. But since this is an experiment, you don't expect all lines, all dots. If you put all dots in that line, if I am your external and practical, I'll straight away reduce marks. That means you have goofed it up. Okay, not it's a rigged experiment. So in proper experiment, 1 or 2 will not lie. So in that case, what we will do, we will draw the line of best fit out here, and we can say that no conductor is a perfectly ohmic conductor. This is close to an ohmic conductor. Did you understand? Means you are finding that the V by I is almost coming same, and then from here, we can have another column where we calculate what is our V by I ratio, and we say this is R1, R2, Rn, R5, and all should be almost same. And then you can take an average and you can say that the R of this is blah blah, the average of this. Did you understand this experiment? In this way, you can actually comment what is the resistance of a particular wire. Okay? So here it becomes very clear that Ohm's law states that the current flowing through a conductor is directly proportional to the PD maintained across its ends, provided temperature. Now, why I'm not using, what is the issue out here? That if you look at the conductor's cross section, you have electrons and you will also have the ions. Ions means the atoms from which the electrons have come out, and there will be collisions among them. These collisions will stop the electrons. Suppose I've asked you, children, the movie has ended. Just walk out of the theater. But you are colliding with everyone. Will you be able to walk out of the theater? No. And I'm watching with the bird's eye view from top, and I see all you 3 children. Rather than getting out of the theater, you're keeping on colliding. Do I get a current from you? No. Current means you all should flow in one direction, drift away, right? So if I increase the temperature, don't you think the kinetic energy of these electrons will increase? So once the kinetic energy of these electrons will increase, what will happen? More collisions will take place. So do I expect you to come out properly? No, you will not come out. So with the increase in temperature, resistance usually goes up. That's why when we define resistance, we always say, or Ohm's law, we say temperature you can't touch, and other physical properties. You cannot make this pen half. Sir, I have not broken the wire. No, you can't change its dimensions. You need to do the experiment in the way you got the conductor. If the conductor was a little bit like curved, keep it that way only and do all the experiments. Is this understood? Right. So based on these two, in grade 10, we also learned that resistance is said to be rho L upon A, and brings a new term called rho, which is known as resistivity. Resistivity. Are you fine till here? So, right, what I will do from now on is that as I continue in this chapter, I will just make a right column, so that in this column I keep writing whatever we discussed. The resistance is directly proportional to length. The first one we discussed. The resistance is inversely proportional to area. Combining, we said that the resistance is equal to rho L upon A, where rho is known as resistivity. Have you understood? Okay. So what we do now, we come across a term called resistivity. Now look. I will no more draw my conductor like a rectangular slab, because a conductor is ultimately a metallic piece of wire. So let's say this is, let's say that this is my metallic piece of wire. Okay, this is my metallic piece of wire, right? This metallic piece of wire will be doing what, beta? It has got a property. It has got a property that is fundamental to it. Fundamental means what happens is that this property does not change irrespective of geometry. You turn it, twist it, curl it, whatever you want, that property will not change irrespective of its geometry. Are you understanding? That property is known as resistivity. We will dive further at it. This is known as resistivity. So what is this, beta? This is material specific, irrespective of the shape, size of that you are taking. Say for example, copper has a particular value of resistivity, which is the resistivity of copper. That's fixed. You want to make out an iPhone wire of it, headphone wire of it, you want to make a big wire of it, the resistivity value does not change. It is something fundamental to it. Got it? Understood? Then what you did, you chose a geometry. So in basic language, you must have chosen some L and some A, where A is your cross-sectional area. Is this understood? Imagining that you have taken something which is very uniform. Let's say we have taken this much of a cross-sectional area, slender, and we have taken a particular length. Right? Now, if you do this, you have a unique article. You have a unique article, and say this article is made up of copper. Now, the size that Neha chose is completely different from the size that he chose, but your areas are same. But our girl Zoe, she chose a completely different size, completely different area. All of you have the same basic material of construction, that is copper. So you all have been gifted with the same resistivity, but you all have created different articles. So you have, once the article is frozen, you give birth to something which is known as resistance. Now this is geometry and temperature dependent. Is this understood? This is geometry and temperature dependent. Is this clear, bacha? So far? And now that you have created your unit article, which demonstrates a particular resistance, let's say it demonstrates a resistance of R ohms. The unit of resistance is ohms, okay? Then this particular article I will call as a resistor. Resistor. So I have a resistor, say something like Rx, which has a resistance of R ohm, made up of a material of resistivity rho. Is this understood? This is very good. See, children all, now when you go, if you are electronics enthusiast and you go to the shop, you go and say, Bhaiya, 10 ohms ka resistance dijiye. Wrong language. You're buying a resistor whose resistance is 10 ohm. I have got so much of mess in my house, you know. Get some laborers, they'll set up your house. Wrong. Get some laborers. Laborers in exchange of money will give labor. Utilizing their labor, you can set up the house. Honest guy shows honesty. Honest guy, honesty. Resistance. Is this thing clear? So let's talk about resistivity then and come back to my formula where I say R is equal to rho L upon A, and I make some assumptions. Say that if L is equal to say 1 meter and A is equal to 1 meter square, so it becomes R is equal to rho 1 meter by 1 meter square, meter square, meter square. But at that time, R and rho are sharing the same value. R and rho are sharing the same value, right? So how do you write? You can write rho is equal to R. The unit of R is ohm, and this is meter. Look, meter, meter square, ohm, meter, right? R ohm meter. Now, are we in a position to define resistivity? Resistivity is the resistance offered by a resistor or a conductor of unit length and unit cross-sectional area. Suppose I have a wire which is 1 meter long and has cross-sectional area of 1 meter square. The resistance that it will offer is called resistivity. You could have chosen a 5 meter wire, but make sure you also choose 5 meter square. Resistance offered by, so it's something like, again, as I gave the example the other day, you today have a separate level of stubbornness, and you right at your DNA have a separate stubbornness that is codified. So I want to find out what is the DNA level stubbornness. So how will you say? The DNA level stubbornness is the stubbornness of one cell of mine. One cell of mine. Resistivity is the resistance offered by a conductor of 1 meter. Rather than that, we'll say unit meter. Unit length, not even meter, we'll say unit length and unit cross-sectional area. Does it make sense? So resistivity is something, child, you cannot change, right? All you can change is how you groom the child in the days to come. So what type of so sometimes I say that, look, copper is the best conductor of electricity. What makes me make that statement? That is because by birth, copper in DNA is a good conductor. So copper's resistivity is low. Now you want to make wires out of copper? You're most welcome. Okay. So it became something like this. Look, I cannot afford copper. I don't have that much money, but I can afford aluminum. But you know, sir, aluminum's resistivity is more than copper. You're not selecting a good thing. Anyways, I can't help it because my budget is limited. At the end of the day, everything has to be techno-commercially feasible. I need to cater to a segment of people who are not going to pay for that iPhone level of headphones. They want the chalta firta headphones. So we have to compromise now. But we need good sound. So now we have to play on the geometry. Now we have to play on the geometry. Have you understood? Is resistivity clear with you? Okay. Chaliye. So this is the formula. Can I wipe out this portion, children, so that I keep maintaining that part? Resistivity is done for us. Okay. Chale. And let's take another new fellow. Come. Our next fellow is known as current density. Current density is denoted by J, but this is a vector. Current density is a vector. Current density. Density is, what is population density? Number of people divided by the area of the place. So current density is current over the cross-sectional area. Now, while current is a scalar, the area is taken as vector. That's why this is known as. So in other sense, we will write J is equal to IA. Is this understood, children? And the unit of J should be a what? It should be ampere meter square minus meter square, or ampere per meter square. So the next formula that we have studied today is current density J is equal to I upon A. And we will be using current density a lot. It tells you what is the density of the current, and it will be along the direction of flow. So this is a what you call vector quantity. Though electric current is not a vector quantity, this is a vector quantity. Okay, and it is a vector quantity. Chalo, so let's see some more relations. We said V is equal to IR. This is one relation we have. Fine. Then we also have a relation R is equal to rho L upon A. Isn't it, children? So if I combine and I try to put this expression out here, I say V is equal to I say rho L upon A. And I arrange it a little bit in a nice manner. I said I get a rho L and I have an I upon A. I upon A we have studied just now. I can say this is rho L and then I can write J. Right till this much. Does your heart agree to it? I by A is J. V is equal to IR, Ohm's law. This is coming from Ohm's law that you studied in grade 10. That's called the macroscopic view of Ohm's law. This is coming from the definition of resistivity. Right? So you have just plugged in this one. And here you have just brought your J is equal to I upon A. So let's see what are the parameters. I say the potential difference. Look at that expression and again start thinking of your that conductor which you had designed. The potential difference across the conductor is the product of the resistivity of the material of the conductor, then the length of the conductor and the current density of that particular conductor. Sir, what is the current density? The current density is the current that is flowing through the conductor divided by the cross-sectional area. Is this much understood, children? Very good. If you have understood this, then I go back to my previous chapter and I say that if there is, okay, what did we learn in previous class? If I have a conductor and there is no electric field, then is there a current setup? Yes, there is a current setup for a small time, after which there will be collisions and everything will die down. So the current, so ultimately we say no electric field, no current. And when you give electric field, what happens? Does the collision stop? No, the collisions do happen. But due to the electric field, this concept should be very clear with you. This is a conductor. No electric field. Do I have free electrons inside it? Yes. Don't they get excited to and attracted to the positive centers? Yes, they do. They will have a lot of collisions. And in this process of collision, what will happen? There will be a random movement. Overall average movement will be zero. There is no current. Given electric field, do the collisions end? No, the collisions don't end. But after giving the electric field, every charged particle, that is the electron, will face a force QE. QE will be EE because the Q is E now. EE, and EE will be opposite to the direction of electric field. So if my electric field is going along the direction of the blue cap, my electrons feel a force now along the. And will they undergo collisions? They will undergo collisions, but all of them ultimately collisions, and they are also drifting. And that drift creates their electric current. That drift happens with the moving with the average velocity. We call it as a drift velocity, and that's what is known as drift current. Have you understood this? So there will always be random motion along with the drift. So if you look at the voltage, now for this voltage to happen, that means right now we have current here, I is there. So electric field must be there. V's value is also, V is equal to ED, means EL from previous chapter. V is always equal to EL, E is equal to V by L. So if you substitute, if you write from these two equations, what can you conclude, children? That EL is equal to rho LJ. Correct? And I cancel L and L, and I write J is equal to rho E. See, your heart agrees or not? Wait, I'll give you time. Just wait till here. Your heart agrees? No issues? Okay. J is equal to, sorry, I think I wrote the expression wrong. J is equal to E 1 by rho. J is equal to 1 upon rho multiplied by E. Sorry, J is equal to 1 upon rho multiplied by E. Agreed? So J is equal to 1 upon rho multiplied by E. Now go back to grade 10. Go back to grade 10. If you still remember. In grade 10, we understood something which was rho, and we called it what? Resistivity. Resistivity. Resistivity is like a bad habit in you. You are being disobedient. It is your measure of your by birth disobedient factor. There is some obedience also in you, right? We should call that obedience as conductivity. In chemistry, when you study electrolytes, in physics, when we study resistivity. Whereas when you study chemistry, in electrochemistry, you'll see you'll always study conductivity, conductivity, conductivity. They study it as kappa. So conductivity is just the opposite. If this is evil, this is God. So God is what? 1 upon evil. Right? And the name for this is given by small sigma. And if this was measured in ohm, this is measured in MHO, mho. Just the opposite of ohm. Nowadays we call it Siemens. And from there that company Siemens comes up, SIEMENS. So we call it conductivity is measured in Siemens. So how do I write this now? I can write J is equal to sigma E. This is a macroscopic viewpoint of Ohm's law. How did you study Ohm's law in grade 10? V equal to IR. Here R, I, R. I got replaced by E. R has got replaced by conductivity. Then V gets replaced by current density. So this is another expression that we need. Our next expression is J is equal to sigma times of E. And from here you can get the value of sigma also. Sigma's what you call unit. Sigma's unit will be J divided by E. So you can note this down. Okay, before you note down, once again, J is I upon A. We know that. V is equal to IR as per Ohm's law. And R is equal to rho L by A. So what I do? I take V, I retain the I, and I punch the R from this value. Why did I do that? Because I can see there is a I and A, and the I upon A is nothing but J. So I bring or I introduce J, and I got L. But L, why did I abolish L? Because then it doesn't become a generic formula. This girl might take some length, this boy might take some length. It doesn't become a generic formula. So you need to abolish that L. So how do I abolish L? I said V is equal to EL. And the electric field will be uniform, whatever you apply. So V is equal to EL, V is equal to rho LJ. So in this place, EL is equal to rho LJ. Ultimately, J is 1 upon rho E, and 1 upon rho is known as sigma, which is conductivity, J equal to. Done, sir, so far? Very good. Once you're done, do let me know, and then I'll wipe off. This clock has become slow and slow and slow and slow and slow. And today, like that LCM problem, it has merged with the right time today. Getting it? This clock used to give erroneous time, but today somehow It has matched with the correct time. Can I wipe this now slowly? Okay, our next topic. Come. Our next topic is drift velocity and what's the topic? Origin of resistivity. It's just a little bit formula centric, that's all. Drift velocity and origin of. So V equal to IR is known to us. Let's see, suppose number one. Okay. Number one, we write, our number one point will be no E, no I. I hope you have understood. Write this, no E, no I. No E, no I. So what happens in this case? Inside conductor, inside the conductor, we have free electrons. They collide with the positive ions, and overall, it's a random motion, and finally average motion is zero. Means somebody is going this way, somebody goes this way, somebody goes this way, collides, somebody this way, somebody this way, somebody this way. This is what is it? Average motion becomes zero. Understood? Now tell me, children, if you, I said no current. If you want to have current, don't you think electrons should move? If the electrons should move, they should have some sort of a velocity. So I am saying, let the velocity of the electrons be something like, say, a vector V, a vector B, V. And it is zero. Zero means what? After all, the average velocity is zero. He moved this way, I moved this way, average velocity. So how do you write it mathematically? I would write that I'm putting up a sigma notation out here, summation, and the summation of a counter I. What is I? I is the velocity of each. I is, he's V1, you're V2, she's V3, I'm V4. Where I varies from 1 to n. N is the number of electrons. And then I am dividing this with, dividing the sum of all those velocities with n. What am I getting? Average velocity. So this is equal to 0. This is the average velocity of electrons is equal to 0. So this is what you need to understand a little bit at a higher level, that when there is no electric field, there is no current. And the no current is because the average velocity of all the electrons taken together is 0. So suppose I had n number of electrons and each n has got an individual velocity, V1, V2, V3. So I said let it be Vi, and I gave a counter I equal to 1 to n. Add all the Vi's and divide them by the total number of electrons, then it should be equal to 0. This is my first understanding. Is this clear? Okay. Point number 1 understood? You can note down and then I'll wipe off point number 1. So this is also an understanding for you that sigma I equal to 1 to n Vi is equal to 0, 1 upon n, when E is equal to 0, I is equal to 0. And you say, why does this happen? The answer for why is actually this. Okay? Bacha, understood? Can I slowly select this up? So under this topic, we will study many subtopics. This was our first subtopic. Aja. Can I? Okay. My next subtopic is the same conductor, and you apply electric field. Now, so many times you are reading the same thing from electrostatics that this will become clear. You apply some electric field, and that how did you apply this electric field? By applying an external potential to the conductor. So as you apply an electric field, then there will be a force experienced by charged particles, and that force is always given by QE, where Q is the charged particle. Have you understood? In the case of a conductor, if I have a conductor and my conductor is a metal, then these charged particles are nothing but electrons. Do you agree? Now, can I write that my force equals to E? I have put a negative, so I'm putting my force as a vector. EE, negative EE. Negative EE means it is actually trying to show that the force acts opposite. So let me make my diagram now. If I see a small section of my conductor, this is a small section of my conductor. So I was having a lot of collision movements of this way. Right? This was here my moving average speed was 0. Further, now I have given an electric field which is in this direction. This is my electric field. Okay. As a result of electric field, I now expect my tiny little electrons to have a force which is EE in this direction. Do you agree? And the combination of both of them leads to something which is known as drift. The electrons will slowly drift. They will collide and they will drift. And this drift is responsible for the current. Is this much understood? Right? So from here we get one more thing. Let's go back to our grade 9. Force F is always given by ma. Father equal to ma ma. So the acceleration of an electron, say A, should be equal to the force, that is EE, right, divided by the mass of the electron, which is m. Hold on, I'll give you time to write. And if you just go by the magnitude, let's go just by the magnitude. See, acceleration always points along the direction of the force. If the force is on this side, the acceleration will also be on this side. If I push you this way, you accelerate. So if I go by magnitude, A should be equal to EE by m. Is this thing understood by you? If so, then please write. And I'm putting my 7th formula out here. The acceleration faced by an electron is EE upon m. How did this come? Force is equal to EE. Force is equal to ma. And from here you got it. Did you understand the negative story? Negative is just when I see it as a vector part. I didn't write what is m. I hope you understand what is m. M is the mass of an electron. M is electron mass. Oh, darling disappeared. Why I broke it down into points, then it becomes easy to absorb. Can I slowly select? Slowly. Arjun, can I take it off? Okay. I should come to point number what beta now? We had third. The first one was no EE, then we give a force. Okay, the third one. Electrons don't accelerate forever. Forever. Electrons don't accelerate forever. Now, if you look at the previous section that we spoke about, we said that the electrons gain an acceleration which is given by charge of the electron, the product of electric field divided by the mass, right? And now you should say, yes, sir, electron has got an acceleration, so electron should accelerate, steady current should fall down. But you are trying to accelerate in old city of Hyderabad where the traffic is very high. What will happen if you accelerate? Accident. So once you gain this acceleration, then what happens? The speed picks up, and if the speed picks up, the collision rate also picks up. And if the collision rate has picked up, then what happens? Once the collision rate picks up, the chicken and the egg story, at the time of collision, the speed will again come to 0. And at this level, the collision picks up, not only the speed will come 0, you may have a different direction change is also possible. Not possible, it does happen. Direction change. It's like on the billiards table. Tuck, now it went on this way, now you collided with somebody. And all these is again giving rise to your same thing, that the moving average is actually 0. So the drift will only continue. What will happen? The moving average part is 0. Have you understood? Electrons gain an acceleration, but with the gain of the acceleration, electron speed does not, you can write, the electron speed does not go up indefinitely. The electron speed does not go up indefinitely. Electrons accelerate, and then there will be collision, and finally we will say collisions. Based on these two, we say collisions reset motion. Yes, you gain speed, you gained acceleration, but I don't expect you to gain huge amount of speed, because then the whole idea of the drift current, the steady current gets lost. So your collisions are only making the average movement getting. Point number 3 clear? So what was point 1? No E, no I. Point 2, with E, F is developed. F is developed, A is developed. Point number 3 comes, A is developed. What happens to V? Doesn't V pick up? No, the A will give you a lot more of collisions. Each collisions will give a reset to your motion. Ultimately, your average motion is 0. You still continue to drift. So A part is taken care of. Right? We are trying to study it, everything in a microscopic level. So the A part is taken care of. Like, chalo. So now, but there is some between one collision to another collision, there was some time available for you to move or to go up. So we bring a new term here, which we say our fourth topic, right? Will be fourth topic? Yes. So we call it the relaxation time. Relaxation time. Have you seen boxing matches? Tap, 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 tap. And then again, suddenly the referee will call out a whistle and just separate the two boxes. For some time, they're just not having a bout. That's relaxation time. So relaxation time is denoted by tau. It is time between two successive collisions. The time between two successive collisions, average is around 10 to the power minus 14 seconds. Did you understand? That is the time an electron is getting between two successive collisions. Brings me to point number 5, where we will now discuss all these. Understood, sir? So see, the story is going so nice now. I have a conductor, no electric field, no current. I gave electric field. I created what? I know if I give an electric field, steady current starts to flow. But what is the reason? I know if I give an electric field, there is a force. Force gives acceleration, sir. How do you nullify that acceleration? Point number 3, we nullified acceleration. Then came point number 4. Between two collisions, there is somewhere the electron will be resting, right? And during that resting time, it is having what? Average speed is 0, but there is a drift speed. There is a drift speed. So let's come to the drift velocity now. Okay. So during tau, what is tau? Relaxation time. Observe me. I am an electron. My velocity is Vd, drift velocity. Drift velocity is denoted by beta Vd. I am an electron, and you understood that drift velocity with which it is drifting. Drift is the combination of both moving average and the electron. I am Vd in time t, speed into time. In time t, that is tau. Don't you think as an electron I moved somewhat ahead? How much? With Vd electron covers a length. Alexa, stop. Alexa, stop. Electron covers a length L, which is equal to Vd into tau. Do you agree or not? Vd into tau. And let me assume that this length is the length of a cylinder. Acha sir, why did you take the length of a cylinder? Hang on, then only you will understand, and then you write. There is a stream of bees which are flying from this part to this part, and they're going like a stream. So many bees together, a volume of bees. And can't I not imagine the bees like a sausage piece or like a cylinder? And they have got a speed of how much? Vd. And their relaxation time is how much? Tau. So in tau interval, they will cover, the bees actually will be moving as a cylindrical block. That's right. And the bees are all your cylinder, so all your electrons. So if that cylinder has got a length L, how much has the bees moved? They have moved the length of a cylinder, which is equal to Vd into L. Distance is equal to speed into time. Is this concept understood? And I say length of a cylinder, and further I say the cylinder whose cross-sectional area is equal to A. So it's something like this. It's something like this. Children, this is not a conductor. This is not a conductor. This is all electrons. All electrons. Out of these electrons, you picked up one small electron, you picked up this. And in tau time, it has actually covered a length. How much is the length it has covered? Vd multiplied by tau. Distance equal to speed into time. And what is the cross section of their stream? A. This is what I'm saying. Agreed? Very good. Chalo, let's go further. So this is my length, and I say that my cross-sectional area is equal to A. So how much volume do you expect? Volume of the cylinder. Cylinder means the hypothetical cylinder of electrons. Volume is always cross-sectional area into pi r square means the cross-sectional area, A into L. So the volume of the cylinder will be AL, nothing but Vd tau into L. Is this clear? Vd tau into L. Right? Fine, this is a volume. Achha, let us also look at the value of Vd. Vd. Velocity. Velocity in terms of acceleration. Acceleration is velocity upon time. So don't you think velocity should be acceleration multiplied by time? So this should be acceleration multiplied by time means, what is the value of acceleration? E by m multiplied by tau. E by m multiplied by tau. Okay, so this means you can write down electrons still move randomly. Electrons still move randomly. We are basically trying to write that same diagram, that random motion and drift. Electrons still move randomly, but superimposed on that random motion, is a small average drift. So the same diagram which you have drawn, so need not draw, random motion plus average drift. And this average drift will cause your flow of current. So in the last class as well as today, what did we say? The average motion due to collisions will be 0, but there will be a drift. The drift is Vd, and we now just found a numerical formula to Vd, and the numerical formula to Vd is what, children? Vd is equal to E tau by m. Have you understood? So, and this one also you keep. This idea is that we'll just use it. This concludes our point number 4. Was this point number 4? I think it was point number 5, right? Yeah, it was point number 5. Sorry. It was point number 5. Take a look, and before I just erase this part. Point number 5 is all understood? Okay, this was all about an electron, okay? But the electrons will be moving as a stream, and the stream can be considered as a cylindrical stream. And that cylinder will have a volume which is equal to A into the length, and the length is always given by Vd into tau. Is this much clear? Okay, now we need to get a generic formula. We need to develop a generic formula for current. Now you've got drift velocity. Now we should get a value for current also. So let's see whether we get it or not. Yeah, fine. So it will be point number 6. So drift velocity is born. So we will now find current due to drift velocity. That means you have to give birth to I due to Vd. Story is clear? They are moving. So we say let n be your number of electrons. How many electrons? N number of electrons. Right? Acha. What was the volume that you found? What was the volume of that cylindrical part that was going? The area multiplied by the length, which was the area multiplied by Vd into tau. This was fine, right? So I'm retaining Vd as Vd, but I know Vd's value is E by m. This is the volume. So total number of electrons will be N A Vd into tau. If this is the volume, how many number of electrons are there? Total is n electrons. N electrons are total number of electrons in the hypothetical cylinder. Okay. N is the number of electrons, A is the cross-sectional area, Vd is the drift velocity. So if you see that entire volume, how much of total number of electrons are going? NEA Vd. N is actually number of electrons per unit volume. This is number of electrons, N with the number per unit volume. Then is this. Okay. Can you now tell me what is the charge value of this? So many electrons. What is the charge of each electron? E is the charge of electrons. So my charge value is N E A V D into tau. N E A V D into tau. So have I 1 minute? 1 minute, children. Instead of tau, 1 minute, one small mistake happened. Instead of tau, did I write tau in that? Just go back into your definition where we had written that relaxation time. Now, just replace that tau. That was my mistake. In a time delta t, just write. In a time, tau is relaxation time, but my mistake. In a time delta t, the length is always equal to Vd into delta t. Sorry, in a time. So these are all delta t. Tau is relaxation time, sorry. So delta t. So NEAVD delta t. No. Delta t is, tau is relaxation time, time between two successive collisions. That has nothing to do with this. I am saying in any time delta t, in any time delta, small instance of time delta t, an electron covers a distance which is equal to Vd into delta t. Any confusion, just let me know. I just don't have the previous screen. No, not like that. See, tau is a parameter which is known as relaxation time. That is the time between two successive collisions. We know electrons will undergo collisions. Forget that part now. Now we are saying every electron is moving. Let's say it is moving for a time delta t. Delta t is an instance of time. While moving delta t, these electrons will be moving like a cylinder. So the length of the cylinder that they are moving is how much? L. L is given by distance equal to speed into time, Vd into delta t. And the cross-sectional area is A. So how much of volume of electrons are going? A into L. Now N is the number of electrons per unit volume. So total number of electrons will be how much? NAVD into delta t. Yes or no? This much is your volume, beta. Each electron carries a charge E. So this is total charge. Now come back to your current. So what is your current? Your current is Q divided by delta T. So your current becomes NEAVD. So this is your formula number 9. Current is equal to NEAVD. So if you know drift velocity, if you know the cross-sectional area of the conductor, if you know the charge of an electron, if you know how many number of electrons are going, you can actually calculate what is the current. This is microscopic current. From you're trying to derive current based on the velocity of an electron, based on the cross-sectional area that they are moving, based on the charge of an electron. Now see, the L has been taken away. The L is no more visible now. Is this fine? Acha, why are we doing all this? We are just trying to define everything in a microscopic viewpoint. Point number 6 also we are done. We're just trying to define everything in a microscopic viewpoint. So 7. Let's see current density now. Current density. Current density was J, which was given as I upon A. So now what is the value of J, children? I is NEAVD divided by A. A cancels A. So I get another formula. J is equal to NEVD. This is the formula for current density. All this we will need in doing problems. J is equal to, very easy, see, NEVD, because J is I upon A. NEVD. Okay, now is the time. Now time, do I have another? Yeah, current density. Yeah, current density is done. Right, so now J is equal to NEVD can I also write J as NE E E tau by M? How did you get it? Velocity. Velocity is acceleration times time. What is the acceleration? EE by M. Force upon mass is acceleration. Multiplied by time. Now this time is relaxation time. Got it? This time is relaxation time. Which means, Zoe, any confusion, tell me. I'll help you out. This is acceleration. Every time you give a force, they will be accelerated. Due to accelerated, they will collide. The moment they are resting between two collision is the relaxation time. So if anybody tells what is drift velocity, that was the definition of drift velocity. Drift velocity is acceleration times. So my J becomes NE square E tau divided by M. Fine. I will just wipe a small portion of it. Give me some time, beta. Little bit time. I'm just wiping this portion off. Okay. And I come to point number how much now? 7. I think 7 we have done. We are at 8. Yeah, we are at 8. So 8 is now defining Ohm's law in microscopic view. 8. 8 is Ohm's law. Now we come to Ohm's law. Did you not see Ohm's law in the previous section as J equal to sigma into E? Yeah. You are also saying that J is equal to N E square E tau divided by M. Right? If I combine these two children, sigma E should be equal to N E square E tau divided by M. Any doubt? Take your time. E cancels E. So sigma is equal to N E square tau divided by M. Okay. And then you write sigma is also 1 upon R. Sorry, 1 upon rho. Rho is what? Resistivity. See, we in Ohm's law, grade 10, you were talking resistance. Resistance is a very subjective thing. Resistance is the particular child. We are not worried about that. We are worried about the DNA factor. So ultimately in grade 12 and all, it is the resistivity that matters to you. 1 upon rho is equal to Ne square tau divided by M. Do you agree? That means rho is equal to M divided by Ne square tau. That is your 11th. Rho is equal to M divided by Ne square tau. Ne square tau. Now ask yourself, is the resistivity, just this, I'll give you time, we'll take time. Is the resistivity a constant? Yes. Look at these terms. Is the mass of an electron constant? Yes. Is N a constant? Yes. Is E a constant? Yes. Is tau a constant? Usually 10 to the power minus 14. Yes, they are constant. So what does this mean? Just see two observations from here. If your N is less, what is N? Number of electrons. If your number of electrons is less, resistivity goes up. Resistivity goes up. Will you be a good conductor? No. No, your resistivity has gone up. If N is less, resistivity goes up. This is typically the behavior shown by insulators. Insulators do not have free electrons. Therefore, their resistivity is very high. So they don't conduct electricity. Okay. See another thing. What happens if tau, tau goes down? Tau goes down. We say resistivity should increase. Now imagine. Tau means time between two collisions have gone down. Time between two collisions have gone down means collisions have become more frequent. two boxes, relaxation time is less, that means they're fighting more. If they fight more, the resistivity goes up, the conductivity falls. So what do you do when you give temperature? When you are giving temperature, you are actually reducing tau. Man. He goes on fighting. When you're increasing temperature, you're exciting them more to fight. The more they fight, the more will the cohesion. So what happens? The time interval between two collisions falls. The resistivity goes up. So that's it. Resistivity, and from here you have got your definition. This is the Ohm's law definition from a microscopic level. Up till here, all okay. If you have any doubt from here, always remember J is equal to, I am again saying, J is equal to sigma into E. This is one definition that we know. And the other definition that we know for J, which you have just found out here, J is also equal to NEVD. J is also equal to NE upon M, and you have a tau. So this becomes equals to NE square E tau divided by M, and you bring sigma E out here. This cancels. Instead of sigma, you write 1 upon R is equal to NE square tau divided by M, and R becomes M by NE square tau. Not that difficult if your funda is correct. Next class, we will do some numerical based on this. And then the chapter will take up Kirchhoff's laws and all. Those are interesting part, the scoring part. Yeah, there will be this chapter is formula intensive. From now on, you will get formulas, but they're very much problems that you will get will be just like cost of a mango is so, find the cost of this. Very realistic problem, not like if a charge is accelerated against not that type of problems you'll get. From now, a theories chapter will come up when we do magnetism, but alternating currents and all, you just get marks. Those are very easy.